Hello everyone. On to 4.7 optimization. This is, in my opinion, kind of a cool section of our course. It's really an applied section. We're trying to optimize certain quantities. So in this first problem, we have a certain amount of fencing, and the question is, what is the largest possible pen that we could make if we were to make 4 pens out of this 850 foot length of fencing that we have. So there must be some geometry, some orientation that if we were to use this 850 foot length of fencing in this specific way, that we actually get the most area for our buck, essentially. So this first problem kind of gives us a set of steps. In general, you might not have all these steps, but these are essentially the steps that you'll be doing in each case. But I just thought it'd be nice to kind of set you up properly for this one. So it says a farmer with 850 foot of fencing wants to enclose a rectangular area and then divide this area into 4 pens with fencing parallel to one side of the rectangle. It says, what is the largest possible area of each pen? So yeah, step 1 says draw a diagram of the general situation. It says introduce notation and label the diagram with symbols. So we have this rectangle, and then the problem said within this rectangle, the farmer wants to construct 4 pens. So I'll just kind of sketch some, not a perfect sketch, but that's okay. So if I label now, it says introduce notation and label the diagram with symbols. So I'll go ahead and call this length X. We have another X there, and there. If I make these evenly spaced, I would have another X here, 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 and here. And then I'll go ahead and call these vertical lengths of the pen, I'll call those Y. So in actuality, to make 4 pens, 1, 2, 3, 4, I actually need 5 verticals, right, to separate them. So this is what part 1 was describing, just a general setup. Step 2 says write an expression for the total area. So if this is our rectangle, then its total area will be a function of both x and y. So when you have a multivariable function, you can go ahead and use comma and then list all the variables involved. So the area would be this length of the rectangle times this length. In other words, length times width. So this length would be x plus x plus x plus x. In other words, 4x. And then this height or width, whatever you want to call it, would just be y. So this would be the area as a function of x and y. Often what we're wanting to do is just get this equation down to one unknown. So that's what part 3 is talking about. So part 3 says, use the given information to write an equation that relates the variables. So now we want to relate x to y. So I know that this problem, we have only 850 feet of fencing to use. So I know that 850 will equal x plus 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 x, right? Because I'm having to use fencing along these outsides, and then I'm having to use fencing in here, so I'll have y plus y plus y plus y plus y. So I'll have, in other words, 8x plus 5y, right? All of these lengths added up should equal 850 if I'm using all of this material. Okay, so this is that equation that they're talking about in step 3. What this allows us to do is in step 4, we're able to now go back. It says use part 3 to write the total area as a function of one variable. So if I have 850 equals 8x plus 5y, maybe I'll choose to isolate y. So if I isolate y, I would have 850 minus 8x divided by 5, just doing some quick algebra. And then what I can do is take this and replace y with it. Okay, so to have that, I'll have now the area just as a function of x would equal 4x times 850 minus 8x over 5. Okay, some more quick algebra. If you simplify that, you can find that a of x is the same as 680x, right? I'm just distributing and combining my terms here, just simplifying our expression here. Minus 32/5 times x squared. So this is our function that we want to maximize. So since I have found this function that I want to maximize, I'll take its derivative. So a prime of x is equal to 680 minus 64 over 5x, just the power rule. Set the derivative equal to 0. And solve for x. So simplifying this, we get x equals, it looks like 53.125, and that's exact. And that would be a number of feet. Okay, so here was our function. This is a parabola that is opening down because of this negative a value. So I know that this x is maximizing. Okay, so once I know x, I can go ahead and plug in x right here to figure out y. So 850 minus 8 times 53.125 all over 5 will equal y. And some quick arithmetic there, y equals 85 feet. Keep in mind what the question was. So it says, what is the largest possible area of each pen? So we have a pen here, 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 and here. So I just found that these are the maximizing dimensions of those pens. So the max pen would be 53.125 times 85, right? In other words, I'm finding the area of just one of these pens, right? X times Y would be the area of this pen. And that comes out to be 4,515.625, and that would be a number of square feet. Okay. On to the next one, page 74. So that brings us to page 75. Okay, so this one says, a box with an open top is to be constructed from a square piece of cardboard. That piece of cardboard apparently is 5 feet wide, and we're making a box out of it by cutting out a square from each of the 4 corners and bending up the sides. It says find the largest volume that such a box can have. So kind of a weird description of this problem. I'll draw a picture for part 1 to kind of further explain what's going on here. So we have this square piece of cardboard, and the idea is that we're going to remove these four corners. That way we'll have something that looks like this. All right, I didn't draw that perfectly, but when we fold along these edges, then we'll have a box that looks something like this. So I'll fold this up, fold this side up, fold the bottom up, right? We're making a box out of this with an open top. Open top. So after that folding occurs, we'll have a box that appears like this. Okay. So now to label, so let's imagine that I made incisions, cuts that were X in length. So we're trying to find basically what depth do I cut into this box to maximize the volume of the box that's generated by that cut. Okay. We had originally that maybe I'll call this side Y, and that would mean that Y is also over here. So after these cuts were made, I have lengths X now surrounding where the corners were, these lengths X. So that means when the folding occurs, this height is X, right? This height of this box would need to be X, right? Whatever the length of the cut, that'll be the height of the box. And since I have cut on both sides, I basically removed some length, right? So the width of this box will no longer be 5 feet because I'm using some of that length to fold up and create the box. So if this length were originally Y, this length is now Y minus 2X because I've removed a length of X from both sides here. So I'm subtracting 2X from the length of the box that it originally had, and also over here, since it's a square. Okay. So I had that the length is 5 feet, right? So I would have that this length of the box, so this length here, would actually be 5 minus 2x. Okay, so I'd have this actually being 5 minus 2x in both cases, because I knew that this original length was 5. So the volume of this box as it originally appeared would have been the volume as a function of x and y would be x times y squared. Well, technically it'd be times y minus 2x all squared. And since I know that this length of the original box is actually 5, I can go ahead and eliminate one of the variables by just calling y equal to 5. So I'll have the volume just as a function of x as x times 5 minus 2x all squared. Right, I'm using the volume of a prism formula. Right, so I'll have the volume as this length times this length In other words, 5 minus 2x times 5 minus 2x. So that's why I have that squared. And then times the height of the box. So this is the volume formula for a box, basically. Okay, so that would actually bring us, this basically would be part 2, part 3 would be essentially relating the length equals the width of the box, which is 5 minus 2x. And then I guess part 4, just to follow these steps as they're laid out, would be what I wrote here. So v of x, I'm kind of just going in a different order. Okay, so once you have the volume of the box written as a function of one variable, now you want to maximize that function. So this will be part 5 finally. So v prime of x. Well, for one, if I had expanded this, just some quick algebra, you can write 25x minus 20x squared plus 4x cubed if you expand this. So v prime would be 25 minus 40x plus 12x squared. Setting this equal to 0 and solving now. So 0 equals 25 minus 40x plus 12x squared. So it looks like the quadratic formula will be needed. So I'll have A is 12, B is negative 40, and C is 25. So I have opposite of B, so 40 plus and minus the square root of negative 40 squared minus 4 times 12 times 25, all over 2 times 12. So after calculating that, you'll see that you have two x's. One of them is 5/2. The other one is 5/6. This one actually doesn't make sense, the 5/2. That'd be 2.5. That would mean that we're cutting halfway into the cardboard, right? So if we're cutting 5 feet across, right? If this is 5 feet across and we're cutting 5/2 into it, then we're cutting half of the box. And if we do that from both sides, then we don't have any box. We don't have any volume. So this one is actually a minimizer. To see that, you could just make a sign chart. So I'll place 5/6, 5/2. Maybe I'll test over here at 0. So you'd be getting plus, plus, plus if you test that into the derivative, right? So this is a sign chart for v prime, by the way. So plug in a 0 here, you get 25. So that would be plus. If you plug in a number like 1 as a test into the derivative, then what do you get? Let me see what you get there. So find v prime of 1, you get 25 minus 40 plus 12. That's negative 3. So in other words, throughout this region, you have a negative, which means that indeed this number is maximizing since I have positive on the left and negative on the right. So 5/6 is your maximal cut. So if I cut into this 5/6 of a foot, then I'm actually going to get the box with the largest volume. Keep in mind, the original question is actually find the largest volume. So once I know that 5/6 is the cut I want to make, now I just need to evaluate the volume at 5, 6. So I'll go back here and I'll plug in 5, 6 for x. So V of 5, 6, if I plug in 5, 6 right here, you'll see that you get 9.259. Let me make a better 5. And 259 actually repeats forever, and this would be cubic feet since we're talking volume. Okay, so on to page 76. I'll do 2 more. I realize these can be challenging, so I'll try to do all but one. All right. So it says, in a beehive, each cell is a regular hexagonal prism. This is a picture of a theoretical cell of a beehive. Open at one end with a trihedral angle at the other end, as in the figure below. So the bees enter through here and they kind of make their home, and they add to the surface of this thing, and therefore they're making their beehive out of a lot of these cells. So it's believed that the bees form their cells in such a way as to minimize the surface area. So they're basically, those bees are doing a smart thing and trying to make the best cell they can, but with the minimum amount of material here. So they have to do as little work as possible to get that cell how they want it. Okay. Examination of these cells has shown that the measure of the apex angle, theta, which is up here, is amazingly consistent. So the bees are good engineers in that way. Based on the geometry of the cell, it can be shown that the surface area S is given by this fairly, intimidating formula. The variable is theta, right? So S and H are actually just constants. S is the length over here, and H is the height or length of this cell. So those are constants. The only variable that we have in this function is theta. So S and H are defined over here. We're supposed to calculate ds d theta. Okay. So for part 1, ds d theta. So I'm going to look here and just go down the line and take the derivative accordingly. So 6sh is a constant, so its derivative with respect to theta is 0. So I move to this one. I do have an expression involving theta here, so we need to figure out what the derivative of cotangent of theta is. So that will be negative cosecant squared theta. So at that step, I'll have positive 3/2, right? Because the negative cosecant can cancel with that negative out front. So I'll just have positive 3/2 s squared times cosecant squared theta for that term's derivative. And then over here, I need to differentiate the cosecant theta. So the derivative of cosecant theta is negative. So I'll just have negative 3s squared root 3 over 2. That whole thing is a constant. The negative derivative of cosecant, I can bring that out front, and then I'll have its derivative as cosecant theta, cotangent theta. So that's actually the derivative. Part 2, it says, what angle should the bees prefer? So now this is when we're optimizing. So I want to set this formula equal to 0 and solve. Okay, So what I'm going to do to make my life a little easier is I'm going to think of things in terms of sines and cosines rather than cosecants and cotangents. So right here, let's see, one sec. So maybe I'll actually factor first. Maybe I'll do that first. So 0 equals, so I'm noticing I have a 3/2 that I can factor out. I can factor out an s squared. And then I can also even factor out a cosecant that's common to both terms. So I'll factor out 3/2 s squared cosecant theta, leaving behind a cosecant theta minus √3, right, that √3. And I already brought the cosecant theta out front, so that just left behind the cotangent theta. So rewriting all that, I can say 0 equals 3/2 s squared. Let's see. And this will be, cosecant will be 1 over sine theta. So I'm rewriting that in terms of sine. And then I have 1 over sine theta here also, minus √3 cotangent is cosine theta over sine theta. So just rewriting everything based on sine and cosine instead of cosecant and cotangent. Okay. Simplifying. So 0 equals, looks like I can factor out a 1 over sine theta. So I'll have 3/2 s squared, 1 over sine squared theta, leaving behind a 1 minus √3 cosine theta. So I factored out the sine theta that was in the denominator. So that turned this 1 over sine theta into 1 over sine squared theta. So maybe rearranging. Okay, so I can rewrite things as, let's see, 3s squared times 1 minus √3 cosine theta all over 2 sine squared theta. Right, so what I did was I left the 3 up top since it's in the numerator. I left the s squared up top since it's in the numerator. I brought the 2 down into the denominator, same with the sine squared, and then left this in the numerator. So the only way this thing will be 0, right, this whole fraction will be 0, is when this thing is 0. Okay, so I now need to figure out where 0 equals 1 minus √3 cosine theta. I'm trying to solve this for theta. So subtract 1, divide by negative √3. I get 1 over √3 equals cosine theta. And use the inverse cosine. So I'm getting inverse cosine 1 over √3 equals theta. In other words, this is the angle that the bees should prefer. Okay, just for our information, it's about equal to 54.7 degrees. So that is part 2. For part 3, so it says determine the minimum surface area of the cell in terms of S and H. So basically what I would need to do, this is the surface area formula here, and I just found the theta that minimizes the surface area. So the actual minimum surface area, the actual value, would be theta replaced with inverse cosine of 1 over √3. Let me grab another piece of paper real quick. So for part 3, I would then have s of inverse cosine of 1 over root 3. So replacing any occurrence of theta with this. So I'm getting 6sh, right? I'm plugging this optimal angle into the original function s of theta that was given. So 6sh minus 3 halves times s squared times the cotangent of inverse cosine 1 over root 3. Plus, I'll just write it down here, plus I'm running out of room, 3s squared root 3 over 2 times the cosecant of inverse cosine of 1 over root 3. So this would be it in terms of s and h. Right, this is just a number, some strange number here, and then times s squared. And this is some number, and then it's times this constant. So really the only unknowns left are s and h here. Okay, so one more. Of course, I'll upload a document with all the solutions here. I'm leaving this one open. Let's go on to example 5. So it says a circular cylindrical metal container open at the top is to have a capacity of 24 pi cubic inches. That's the volume it should have. The cost of the material used for the bottom of the container is 15 cents per square inch, and that of the material used for the curved part, in other words, the lateral side, is 5 cents per square inch. If there is no waste material, find the dimensions that will minimize the cost of the material. So it doesn't give me like part 1, part 2, part 3, part 4, but still those parts are good to appreciate. So I will draw a picture just to get things started. So I have this circular cylindrical container. So there's my picture of that. Here I will have its radius r. Here I will have its height h. Okay, and just to notate it, this top is open in this case, so that will change our calculation. If it were to be a closed top, then I would have more cost involved because I would need to enclose this. But since it's open, I don't need material there. Okay, so basically that figure could kind of deconstruct into a circle of radius r, and if you were to kind of like slice the side of the can and then kind of flay it open, what you would have is this rectangle, right? If you just imagine slicing a can of Coke down the height of it and then splaying that open, you get this rectangle for which this length will be the distance around the circle, right? Because this length was originally associated with the can going laterally all the way around. So I'd have 2 pi r, the circumference of the circle, as this length. And then I would have h as the height of that rectangle. So if I want to minimize the cost, what I need is a cost function to minimize, right? That's what's been true about all these, is if you want to minimize surface area, you need a surface area function. If you want to minimize, what was the other one? Oh yeah, if you want to maximize the area, for example 1, these pens, you need an area function to maximize. Once you develop that function, you take its derivative, set it to 0, and so on. So we need to develop a cost function here. So the cost to make this portion it said the bottom of the container is 15 cents per square inch. So the cost here, just to make this circular part, would be 15 cents times pi r squared. In other words, the area, right? This is the cost per area, this is the area, so this is now just the cost, right? Cost per area times area equals cost. The cost for this piece over here, well, it said the material used for the curved part is 5 cents per square inch, so I'd have 0.05, and then times 2 pi r h. Okay, right, here's the cost per area, here's the area, right? The area of this rectangle would be 2 pi r times h, length times width. So the cost of the entire product would be a function of both r and h, and you would have 0.15 times pi r squared plus, I guess I'll just write it, so 0.5 times 2, I'll just write it as 0.10 times pi r h. Right, this would be the cost of the can in terms of both r and h. So we want to eliminate one of the variables. I have not used this information yet, so I know that the volume of this can should be 24 pi cubic inches. So 24 pi should be equal to the volume of the can, which would be pi r squared times h, the volume formula for a circular cylinder. If I divide both sides by pi r squared, I can eliminate h from the cost function. So this would mean that 24 over r squared equals h. So I can now take this and represent h with it. So now the cost, just as a function of r, would be 0.15 pi r squared plus 0.10 pi r times 24 over r squared. I can cancel an r, I can multiply 24 times 0.1. So just to simplify this a bit, I get 0.15 pi r squared plus 0.1 times 24 is 2.4. R divided by r squared is 1 over r. So I will write that as pi times r to the negative 1. So this is our cost function just with respect to the radius of the can. Once you have your function that you're interested in optimizing, in this case we're trying to minimize, then take its derivative. So C prime of r, I'm taking this with respect to r, so power rule, multiply down the 2, I get 0.30 pi r. Power rule again, multiply down by negative 1, I get minus 2.4 pi r raised to the negative 2. I will factor this. So in factored form, we can write, well, I'll factor out a 0.30, a pi, and an r to the negative 2. Doing that, we leave behind r cubed minus 8. So simplified, I have C prime of r would be 0.30 pi times r cubed minus 8 all over r squared. we want to set this derivative to 0. So I'll have 0 equals 0.3 pi r cubed minus 8 over r squared. All right, now trying to figure out when this thing equals 0. This thing will only equal 0 when r cubed minus 8 equals 0. So I'll just focus on it. Solving that means we want the radius to be 2 inches. Right? There is a solution. Well, I'll not say that. Never mind. So here's the radius we want to use. Keep in mind the original question is find the dimensions. So we're looking for both r and h for this. Once you find, though, the radius, you do need to make sure that this does minimize. So I'll do a sign chart. I'll place 2 on here. Maybe I'll test with 1. And by the way, this is a sign chart for C prime. So I'm plugging in 1 into C prime. If I plug in a 1, it looks like I get a negative result. If I plug in a 3, something over here, into C prime, I will get what? A positive result. So I'm taking that 3 and plugging it into C prime, just caring about the sign of it. So this means that we're negatively sloped and then 0 and then positively sloped on the right of 2. So this is a minimizer, this radius. Okay, so once I know the radius, well, as soon as I know the radius, I can plug it in here, and then I can quickly solve for h without much difficulty. So by the way, this is the radius we want to use for the can. And then h equals, that was 24 over r squared. So in this case, 24 over 2 squared, in other words, 6 inches for h. All right. Talk to you soon.